Hello, ladies and gentlemen. We are C3. Welcome to our presentation. Today, our topic is assessing the risk of the technology. My name is Tinghao Shi. Here are my teammates Yuxing and Zhipen. You will dispute that nowadays, technology has changed the life of the general public. One typical example is a smartphone. You can find people present here always carry one smartphone, or maybe someone even has more than two. Yes, mobile phone has changed the way people interact, which is convenient, because it makes instant communication come true, especially for people who are far away from each other. However, it seems that few would view the mobile phone as a bomb until the battery of the Samsung mobile phone exploded. Technological disaster of this kind shows the way that is used to assessing the deficiency in technology is inadequate, and more concern is needed. So, in this presentation, we will focus on two main methods for assessing risk. That is the probabilistic risk assessment and the risk cost-benefit analysis. And overall, the task is how to reduce the number and the magnitude of the technological disaster. So we must reform the method of evaluating the potential impact of technology and develop more effective methods. Okay, it's your turn, Yuxing.
Probabilistic risk assessment, as known as PRA, or quantitative risk assessment, as known as QRA, attempts to provide a model of causal interactions of the technological system under study. The goal of PRA is to supply a mathematical technique for estimating the probability of events that cause physical damage or loss of life. A comprehensive probabilistic risk assessment involves three steps. First is the identification of events that lead to or initiate unwanted consequences. The second is the modeling of identified events sequences with respect to probabilities and the consequences. And the third is the determination of the magnitude of risks and harm involved. PRA has become one of the standard methods used by engineers for determining the likelihood of an industrial accident or a technological disaster. This method makes use of technical procedures called value tree analysis and event tree analysis. In an event tree analysis, one begins with an initial event, such as a loss of electrical power to a nuclear power plant, and using inductive logic reasons forward, trying to determine the state of the system to which the events can lead. The analysis therefore begins with the initiating event that a coolant pipe might break. If the pipe breaks without any other system failing at the same time, then the probability that there would be a radiation release is PA, a very small release, as shown in figure. Possible failures are next defined for each system, and accident sequences are constructed, consisting of initiating event with specific system failing and a specific system succeeding. For example, the probability of both a pipe breaking and the corresponding loss of electrical power to the plant is PA multiplies PB, would lead to a very large release of radiation. In a fault-tree study, the analyst begins with a hypothetical undesirable event, then using deductive logic reasons backwards to determine what might have led to the event. Fault trees follow a cause and effect model and can be used whenever hypothetical events can be resolved into more basic, discrete units for which failure data exist or for which failure possibilities are generally easily calculable. This figure illustrates a fault tree for analyzing the possible causes of why a car would not start. For example, a good mechanic would, more than likely, already be aware of all of the possible reasons of why a car will not start. The mechanic would then construct a fault tree as illustrated in the figure, checking each subsystem as a possible cause of why the car will not start. An insufficient battery charge is the most likely cause of a car not starting, so the mechanic would begin there and proceed to check whether there was a faulty ground connection, the battery terminals were loose or corroded, or the battery charge was weak, etc. Since the first comprehensive application probabilities risk assessments in 1975, the U.S. reactor safety study, more than 15 large-scale PRA have been carried out for nuclear power plants in the United States. Even though PRA has been used extensively, there are substantial methodological problems, some of which we will now consider. The first set of methodological problems in PRA arises when experts attempt to determine which factors to exclude and which part to include. The second set of problems arise when scientific uncertainties appear in the modeling process. Thirdly, there are reservations about the adequacy of the method due to uncertainties that arise in attempting to trace out unknown cause and effect relationships. A false deficiency of the method is its inability to account for uncertainties that inevitably arise due to operator error and other human factors. Fifth, the very complexity of many large-scale technologies render the PRA method inadequate as the sole source of assessing risks and the adequate safety level. This figure lists the 5 problems pertaining to PRA and associated issues that arise with each problem.
Now let's talk about our second topic, risk cost benefit analysis. Along with the PRA cost benefit analysis, CBA, and risk cost benefit analysis, RCBA, arose as a preeminent method of assessing the risk of technology during the late 1960s and early 1970s. As Congress began to enact legislation on the regulation and monitoring of technology and social and environmental impacts, it requires the government agency to consider technical and economic feasibility characteristics and health and environmental effects when contemplating the technological interventions. It is widely used concerning controversial problems such as storage and disposal of nuclear waste, some medical economies for assessment of medical inventions and other healthcare contexts. It is also widely used in analysis of policy making concerning environmental toxins. It also used for large-scale water and waste management technology. It looks like good method for risk-cost-benefit analysis. However, it has some methodological problems associated with RCBA. The first one is it is unquestioned assumption. It's an unquestioned assumption that all significant consequences can be enumerated in advance. Which the assumption is that all of the costs and benefits of the particular implementation of new technology or extension of a non-technology can be clearly identified and cataloged, that meaningful probability, cost, and benefit values can be obtained and assigned to them, and that often disparate cost and benefit and can somehow be made of comparable on one another. The problem is that what will be included and what will be excluded, and certain steps to how one should define the harm or risk of a particular action for the analysis to make judgments that are relevant. The second problem of RCBA is that the assignment of a monetary value of human life, a necessary requirement of a robust risk-cost-benefit analysis. Is this of all the difficulties that surrounded the template to calculate the economic value of life, one of the theorems is the moral one, namely whether it is morally permissible to place any price on human life. Its problem is how much is it worth to prevent a death of a person. This question has no answer. It has some saying that life and risk of life is some measurable quantity that actually exists in the stable and determinable way. In other words, suppose that the higher and the lower wages people, except for different types of jobs, are interpreted as a valid measure of the cash value people are thought to place on their own lives. The cheap life in some poor neighborhood or less developed nations is very common. For the third problem, RCB is how to deduce the value attribution of all the identified risk, cost, and benefits. This is evident in willingness to pay. Take, for example, how much is a beautiful view worth in the monetary terms, or how much is a landscape worth? How about a sunset? Or how much would someone be willing to pay to avoid having a toxic waste dump or power plant or an oil refinery built in his or her community? And the fourth problem is RCBA becomes visible when one begins to probe the unquestioned assumption that market values provide the best opportunity for human beings to advance their life goals. In other words, an RCBA methodology makes the assumption that the decisions people make in the marketplace are rational with regard to price, needs, and wants. However, it must be admitted that even in the open market, the notion of the utility maximization does not fully satisfy the variety of human needs and purposes. For the last problem is that besides the RCBA method are the well-known criticisms that RCBA fails to address adequately issue of fairness associated with the equitable distribution of risk and harms. The problem is who pays the cost and who gets the benefits. The goal is to determine within the limited definition of the goods and harms involves the net good or harm that their technological invention will produce. For example, if an oil refinery in the neighborhood can be calculated to allow millions of distant persons to benefit from the gasoline and other products of that refinery, it can be multiplied into a major benefit. On the other hand, if a refinery results in a higher cancer rate, great medical costs, and the residential property devaluation in the immediate neighborhood, it can also be calculated a part of the net cost or harms and subtract from the great good. Although the net benefit may greatly outweigh the overall cost, the distribution of the goods and harms may be not fair. Another thing is just across the geographical, economic, and social space is a crucial side of values of RCBA leaves out of the calculations and equations.
However, PRA and RCBA are not the only way to assess the risks and harms of the technology. There is another approach called technology assessment, which maximizes the public utility and considers the possible impact on different stakeholders, whether the impact is good or bad. Now, it's time for us to draw a conclusion. In order to enhance our capacity to prevent technological disaster, a broader concept of technology assessment is needed. It should involve social and constituent impact and multidisciplinary analysis ranging from economy to society, as well as from ethics to politics. As a result, it can be a very useful policy-making tool. Without it, there will be a bleak prospect. Thank you for your attention.